All right, today we're looking at graphing square root functions. And as we approach this thing, we're going to approach it the same way we've approached graphing almost anything. We're going to start off with basically an XY chart just to kind of get a feel for what these things look like. And the fact of the matter is we kind of already know what they look like based on the inverse. When we talk about the inverse function of an x squared or a quadratic function, we kind of get this sideways looking parabola, and that's what square root functions are, okay? They're the inverse of a quadratic, and so we get this kind of parabola that opens left and right instead of up and down. And typically it's half a sideways parabola, but we're going to start off with a table of values. We're going to graph these things, and once we have a basic understanding of this, we're going to use the fact that we know any function can be shifted and moved to left, right, up, and down, can be stretched and shrunk to kind of help us graph the rest of these. So when I look at this guy, typically when I start off an XY chart, I always start with the same couple values. I usually start with these values, -2, -1, 0, 1, and 2. But there's an issue with starting with these values this time. As I go to plug these in, when I plug the -2 in, if I plug a -2 in, the y value gives me as an I root 2. All right? And the issue there is I can't plot an imaginary number on my coordinate plane here. So really, imaginary numbers are kind of useless here in terms of graphing. So I really don't want the -2. And in fact, I don't want the -1 either, because I can see right away that that's also going to give me an imaginary solution. So be very careful when you pick your x values here. I'm going to start with an x value of 0 and then plug in 1, 2, 3, and 4. All right? And so I plug this in, I plug a 0 and I get a 0 out. I plug a 1 in, I get a 1 out. If I plug a 2 in, that's a job for my calculator. That's going to give me like a 1.4. If I plug a 3 in, again, I plug it into my calculator. It's going to give me about a 1.7. If I plug the 4 in, it gives me a 2. And so now I'm just going to go ahead and plot these. So I'm going to graph it. I've got 0, 0, the 1, 1, 2, 1.4 is about here, 1.7 is about here, and then the 2 is about there. Okay? And I could keep going if I wanted more values here, but I can kind of get an understanding of what this thing looks like. It looks like a curve, and it looks like half of a sideways parabola here, and so that's what I graph. All right? This is my standard square root function. Just like when I graphed parabolas for the first time, I looked at y equals x squared, and I memorized that pattern with y equals x squared. It was over 1 up 1, over 2 up 4, over 3 up 9. I'm squaring each of the values. Here, I do the same thing. I memorize this pattern, and it's easy to memorize the pattern in terms of square roots. So it's over 1 up 1, because the square root of 1 is 1. It's over 4 up 2 because the square root of 4 is 2. The next logical one to do would be 9 over 9 up 3, over 16 up 4. The other interesting thing is if you kind of turn this on its side, it follows the same pattern as our parabolas. Remember, the parabolas were over 1. If I show it this way, the parabola was over 1 up 1. Over 2 up 4, which is what this is doing. It's literally our sideways parabola and follows the same type of pattern, okay? So we kind of commit this pattern to memory, we understand how it works, and then what we're going to do is we're going to shift this thing around using that pattern. For example, when I look at this guy, I should be able to recognize right away that if I add 3 on the outside, it's going to raise my function up 3. So this is going to be the same thing, but instead of starting at 0, 0, I'm going to start up here. I switched colors. Let me try again. I'm going to start up here at 0, 3. And it's going to follow in the same pattern, over 1 up 1, over 4 up 2. And if I wanted to fill some others in, I'd have the up 1.4 and the up 1.7. But I get this exact same shape that I had before. It's absolutely no different from the example above, except the whole thing's been moved up 3 units. All right, and so when I plug this in, if I start with something like 0, 1, 2, 3, and 4, if I were to plug these in here, I'd get a 3. Here I would get a 4. Here I'd get a 4.4, a 4.7, and a 5. Okay, and it's not that I'm plugging those in extremely quickly, but look at the ordered pairs that I had the last time, and see everything's moved up 3. See, if I add 3 to this guy, it gives me my first ordered pair down here. If I add 3 to this guy, add 3 to this guy. I'm moving each of these up 3, and that's what gives me these values down here, okay? So by doing that, I'm just kind of shifting this whole thing up 3. The other way to look at it is think of it in terms of vertex. This is kind of like in this format, y equals a times the square root of x minus h plus k. See, everything that we've done in here kind of prescribes to vertex form. When we think of the other vertex forms that we've had a couple of them. We've had y equals a times the absolute value of x minus h plus k. And we've had y equals a times x minus h squared plus k. But they all work on the same basic principle. Yeah, the vertex is hk. It's always the opposite of what's there with the x, and then what's outside with the y just as it is to give us our vertex. So this one, you can see the vertex is 0, 3. But it works on the same basic principle that when I add or subtract inside with x, it moves left and right. And it always does the opposite of what we might think. When I add, I move to the left, and when I subtract, I move to the right that many units. On the outside, it always moves us up and down. When I add, I move up that many units. When I subtract, I move down that many units. And so the vertex is, of course, those values, because I'm basically starting at 0, 0, and I'm shifting left, right, up, and down that many units, which brings me to a new ordered pair, which matches the values that are written there, okay? So they're all working on the same basic principle here. Even the a value is working on the same basic principle. A value is positive, this thing opens up, and it's a 1, so it's my standard shape. If I change it to a 2, I'm going to stretch it. If I change it to something else, I'm going to shrink this thing. And I'm basically going to change the heights of this to get a new shape, all right? So kind of think of it like vertex form with the other things we've dealt with, because we're moving and shifting this thing in the same way, okay? For example, if I look at the next one. Again, if I think of this in terms of vertex, I can think of the vertex as being like 2, 0. And again, when I'm inside with the x, if I subtract 2, I'll move to the right 2. And look at where this thing ends up. It's to the right 2. See, I'm shifted the whole thing over. The a value is a 1. See, there's a 1 out front. So this thing is going to open up, and it's going to be my standard shape. So over 1 up 1, over 4 up 2. And now, of course, I could fill the values in between if I want, but I still get this exact same parabola, this exact same size and shape, but it's just been moved over 2. Okay? And once again, if I were to start plugging values in, think about the lowest value I could plug in this time. Before it was 0. Now the lowest value I can plug in without getting an imaginary number is 2. So I would start with 2, 3, 4, 5, and 6 are probably the values I would plug in, and look what I get. 0, 1, 1.4, 1.7, and a 2. Okay? Because it's following that same shape, so I get those same y values. All right? If I look at the next one is following the same basic principle. This has a vertex of 0, 0. But this time, because there's a negative 1 out front, see, this is a negative 1 that I have here. So this thing is going to open down, but because it's still a 1, it's going to follow my standard pattern. But instead of over 1 up 1, I go down 1 instead. Instead of over 4 up 2, I go down 2 instead. So the only change that happens here is this thing opens down instead of up. And I still graph my parabola the same way. Okay? So, or my sideways parabola the same way as my half a sideways parabola, my square root function, all right? But it's the same shape, the thing's just out opening the opposite direction. And think about that, if I use those same values that I've been using, it's going to give me the same values over here, but every single one of them is now going to be negative because of that negative that's out front, okay? If I look at this guy, it looks like it's got a vertex of 0, 1. Okay, so the vertex, if I label that, that's 0, 1. Again, because nothing is happening inside with, 0, negative 1. Nothing is happening inside with the x, but there's a minus 1 on the outside, which means this whole thing is going to be shifted down 1 unit. So my vertex is going to be right here. The a value is 2, so this thing is going to open up. And because it's a 2, it's going to be stretched vertically. So let me draw my original function. My original shape would be over 1 up 1, over 4 up 2. But basically, since I'm stretching this by a factor of 2, I'm going to double all those. So right here, instead of going up 1, I go up 2 instead. Here, instead of going up 2, I go up 4. So I kind of get this, instead of this shallow parabola that I've been dealing with, that's my original shape, I'm going to get this thing that's a little bit taller, that's actually twice as tall. Okay, it's been stretched vertically, and that's it. And there's really no need at this point to continue doing the XY chart, and that's the point. We want to get away from this XY chart because there's better ways to do it. There's faster ways to do it, and this is it, okay? We take that standard shape and we stretch it and move it around a little bit, okay? If I look at the next one, this is the one shift that we didn't have when we did parabolas and when we did absolute value functions. Okay, so this one's just a little bit different. I'm still going to do the same things that I've done before, but now I throw a negative on the inside. And so think of it this way. Remember, a negative on the outside, when I put a negative out here, making it positive or negative, it affects whether the function opens up or down. So if I put a negative inside where x is, it's going to affect whether this thing opens to the left or to the right. And that's what happens here. See, I'm going to have my same shape, but instead of opening to the right, I'm going to open to the left. I'm still going to go over 1 up 1, over 4 up 2, but I'm going to open in this direction instead. Okay? And so that's the effect that this thing has, is I open to the left instead of the right. And that makes sense because think about the values I can plug in here. I can still plug in 0, which gives me a 0, but I can't plug in a 1 because that's going to become negative when I plug it in. So I have to plug in negative numbers because when I plug negatives in, they'll become positive. See, I'm plugging in -1, -2, -3, -4. And when I do that, I get all the same positive values I got before, but I'm plugging in negative values to get those. All right? And that's why this thing opens to the left. It uses those x values instead. And the reason we never saw this with parabolas or with absolute value functions, if I look at a parabola, here's a parabola. If you were to shift this thing left to right, flip it left and right, my new parabola is going to be this. And see how it's no different from the original? Okay, flipping it because it's already symmetrical in that direction doesn't change anything. And it's basically graphing this, y equals x squared, graphing this, y equals negative x squared. And really there's no difference there because negative x squared is actually positive. When I square a negative, it becomes a positive. So those graphs are the same, which is why we never really discussed this before. Same thing with absolute value. Because absolute value is that V shape, it's already symmetrical in that way. If I were to flip this thing left to right, it doesn't change anything. And that makes sense, again, if we think about it from the perspective of the equation, y equals the absolute value of x versus y equals the absolute value of a negative x. Well, those are exactly the same. The absolute value of negative x is going to be positive no matter what, just like the absolute value of positive x, okay? And so we never saw these kind of left to right, these horizontal flips before because there was no need to see it, all right? But now we can clearly see a value on the outside affects whether it opens up or down. The a value essentially on the inside affects whether it opens left or right. Okay, so we have the same basic shifts that we've had before. We can identify the vertex, the left, right, up, and down shifts. We can identify the direction of opening vertically by the a value and whether it's going to be stretched or shrunk. And then we can identify whether it's going to open left or right based on the leading coefficient inside where x is located. Okay?